Let's look at a few examples now. Imagine that these are synthetic problems on the next quiz or exam. And in this case, I think there'll be no restrictions on what you can use. So how do we affect this synthesis? We see that there are no functional groups here, but we have probably the same skeleton structure. We've got a 2-carbon chain hanging off our 6-membered ring. This is still sort of a 2-carbon chain. We've just added, it appears that we've added these 2 methyl groups. And if we imagine that we had a carbonyl right here at some point, this would be a alpha alkylation, this would be a beta alkylation. So we just talked about that. One of them could be added via a cuprate reagent, the other could be added via methyl chloride to work up that cuprate reagent intermediate. So let's look at this. We can remove the carbonyl that we need at the end of the reaction very easily with, let's use the Wolff-Kishner. So KOH and hydrazine and heat will remove the aldehyde. This aldehyde now is more clearly showing us that we've added a carbon at the alpha position and we've added a carbon at the beta position, and we can do that in a 2-step sequence. Adding the methyl cuprate, working that up with methyl bromide or methyl chloride, and all we need is the alpha-beta unsaturated version of that aldehyde, and I hope you see how this aldehyde is basically the same as what we started with. A little PCC to oxidize to the aldehyde, then we can add 1 methyl group here at the beta position as a nucleophile, then we can add another methyl group here at the alpha position as the electrophile, that's these 2 methyls, and then our end product has no carbonyl, so we can remove the carbonyl altogether using the Wolff-Kishner. Here's another example. So in this case, we see we start with 4 carbons, and not 100% of the time, but it's pretty likely that this carbon is the same as this carbon, and so this alcohol used to be our aldehyde, and thus these 4 carbons are the starting material. You can see how we've created a new bond at the alpha carbon on our aldehyde. So we've created a new bond, and we've somehow added this phenyl group. That phenyl group is added to the beta position, so we can look at adding 4 carbons, maybe doing an aldol condensation. That's probably the easiest way to add 4 carbons because we started with 4 carbons. So if we do a self-condensation, we can get something that looks like that. And you can see now that we've added 1, 2, 3, 4. I still need to make the alcohol, and I still need to add the phenyl ring. The phenyl can add right here, and that's going to be a conjugate addition. That gets me to this intermediate, and of course one more step, NABH4 will reduce the aldehyde to the primary alcohol. I would like to point out that we don't need to stop here, right? We know plenty of reactions of primary alcohols. We could turn this into an alkyl chloride, so we could turn it into a chloride. I could have turned this into a carboxylic acid and done some reactions with that, maybe ended up with an ester right there. Anything we know how to turn alcohols into, we can keep going. So we can make this much more complex. We can make this into an alkene. We could make this into an ether, right? We know how to turn alcohols into ethers. So there are a lot of possibilities that we could do with our product in this case. Perhaps this is just an intermediate on the road to something bigger and better. Let's look at one more sample. So in this case, we should take a look at the relationship of the functional groups. Recognize that they are both carbonyls, So this is a 1,5-dicarbonyl species. 1,5-dicarbonyl species. And so that tells us it's probably a Stork enamine synthesis, where we would create the bond between carbons 2 and 3 via the enamine attacking a Michael acceptor, and maybe the whole piece here is going to be our Michael acceptor, where we'd have a double bond between 3 and 4. So let's make our enamine. And let's react that with a compound that has a double bond between 3 and 4, along with the carbonyl, 2 methyl groups off of carbon number 3. Right, so just if you're keeping track at home, these are the numbering: 1, 2, 3, 4, 5. Those are the same numbers that I have in my product. And when I mix these together, and the first step would be mixing them, the second step would be mild acid workup. That would hydrolyze our imine, protonate the enolate that's formed. We would go directly to the product there. Now we could do some more chemistry with these ketones. However, most likely we'd have to do the same chemistry on each ketone, because it's going to be very hard to differentiate these two, given that they're both ketones, they're both approximately the same level of reactivity, and they're both approximately the same level of steric hindrance. So I'm not sure we're going to be able to isolate, say, ketone number 5 and react that with a Grignard or reduce it or turn into an acetal without affecting anything at ketone number 1. So typically this might be our final product, or at least until we're more advanced synthetic chemists, this might be as far as we can go with this Stork enamine synthesis. But we could imagine starting with maybe a cyclopentene that we would then have to somehow turn into cyclopentanone that we could then do a Stork enamine synthesis with. We could imagine starting with the alcohol, that we could do the same thing basically, or a chloride. So we could do a lot of things. We could even have, if for some reason we didn't want to be atom economical, we could even have to cleave off those 3 carbons to make the cyclopentanone that we could then do our Stork enamine synthesis with. So we don't necessarily have to start with a ketone in order to have discovered that we need a Stork enamine reaction. We could take any sort of starting material, recognize that these are all equivalent to ketones with 1 or 2 simple steps, and then recognize that we have a 1,5-dicarbonyl species as the product, and that maybe at some point we need to make a ketone to turn into an enamine to react with a Michael acceptor to get to our 1,5-dicarbonyl product, even though we're not starting with any sort of carbonyl. So we should begin to start to be able to just mentally and quickly turn these functional groups into other functional groups with 1 or 2 quick synthetic steps.